An aircraft can break into thousands of pieces, fuel can ignite, metal can fold under enormous force, and most electronic systems can be destroyed within seconds. Yet somewhere inside the wreckage, investigators may find one small device capable of reconstructing the final moments of the flight. It can survive an impact thousands of times stronger than gravity, remain sealed inside an intense fire, and preserve its data beneath thousands of meters of ocean water. So what is protecting the information inside it? And why is one of aviation's most famous devices not actually black? It is commonly known as the black box. But inside a modern commercial passenger aircraft, there are usually two separate recording systems. The Flight Data Recorder, or FDR, stores information about how the aircraft was operating. The Cockpit Voice Recorder, or CVR, captures audio from the flight deck. Neither device controls the aircraft or prevents an accident. Their only purpose is to continuously preserve evidence, even when almost everything around them is destroyed. The recording process begins with the aircraft sensor network. Sensors distributed across the engines, wings, landing gear, fuselage, and aircraft flight control surfaces constantly measure the aircraft's condition. They monitor altitude, airspeed, heading, acceleration, engine performance, control positions, and many other parameters. These signals are sent to the Flight Data Acquisition Unit, or FDAU. It receives information in different electrical formats, organizes it into a synchronized data stream, and sends it to the Flight Data Recorder. The FDR continuously records this information. When its storage becomes full, new data replaces the oldest data, preserving the most recent portion of the flight. Modern systems can record hundreds or even thousands of parameters, allowing investigators to reconstruct how the aircraft moved and how its systems responded during the final moments. At the same time, the Cockpit Voice Recorder receives audio from the cockpit area microphone, pilot headsets, and the radio communication system. It captures conversations, warning tones, switch movements, mechanical sounds, and changes in background noise. A sound that appears insignificant may reveal when an alarm activated, when engine power changed, or when the crew first recognized a problem. But collecting the data is the easy part. Keeping it intact through a violent accident is the real engineering challenge. The orange enclosure visible from the outside is not the most important part of the recorder. The critical component is the Crash Survivable Memory Unit, or CSA. At its center is the solid-state memory chip stack. Unlike older magnetic recording systems, solid-state memory has no spinning disk or moving read head that can break during impact. Around the memory is a carefully engineered sequence of protective layers. A stainless steel protective shell resists crushing and penetration. An impact-absorbing layer reduces the shock transferred toward the center. High-temperature thermal insulation slows the movement of heat toward the memory chips. These layers work together as a compact survival chamber for the data. The CSA is designed to tolerate an impact of approximately 3,400 G for a few thousandths of a second, but surviving the collision is only the beginning. A post-crash fuel fire can expose the recorder to temperatures near 1100 degrees Celsius. The insulation cannot stop heat forever. Instead, it delays the temperature rise inside the unit, protecting the memory long enough for the most intense phase of the fire to pass. Recorders are normally installed inside the aircraft tail section, one of the aircraft's most crash-survivable areas. From there, they operate continuously while the aircraft is powered, quietly storing information that may never be needed. But if the aircraft falls into the ocean, different problem begins. Attached to each recorder is an underwater locator beacon, or ULB. When water bridges its activation contacts, the beacon automatically begins producing an acoustic pulse at 37.5 kHz. A hydrophone search system can listen for these repeating underwater pings and guide search teams toward the recorder. However, the beacon does not transmit the stored flight data. It only produces a locating signal. Its battery also has a limited operating period. If the search area is enormous, the water is extremely deep, or the recorder becomes buried in sediment on the deep ocean seabed, the signal may be difficult to detect. The beacon can even be damaged or separated during the impact. This is why a recorder may remain missing for months or years without necessarily losing the information stored inside it. A deep-sea recovery vehicle may eventually locate the recorder among scattered pieces of the aircraft wreckage field. Once recovered, the device must be handled carefully. A recorder raised from salt water may be kept submerged in clean water so that salt and debris do not dry onto its internal components and cause additional damage. The Air Accident Investigation Team then transports it to a specialized laboratory. The crushed outer enclosure is removed and the CISA is opened under controlled conditions. If the electronics remain functional, the information can be downloaded through a recorder data readout station. If the recorder is severely damaged, technicians may remove the solid-state memory chip stack, clean it, and connect it to compatible equipment designed to recover the stored data. But the black box does not announce the cause of the accident. Investigators must combine the FEDR data with CVR audio, radar information, air traffic control communications, weather conditions, maintenance records, and physical evidence. These sources are synchronized into a flight reconstruction timeline. The aircraft's movements, system warnings, pilot actions, and cockpit sounds can then be examined in the exact order they occurred. A single parameter rarely explains an entire disaster, but when thousands of measurements are aligned with the final sounds from the cockpit, the beginning of the failure sequence may become visible. Investigators can determine what changed first, how the aircraft responded, and why the crew may not have been able to recover. And this reveals the central paradox of the black box. It is not designed to save the aircraft that is already fallen. It is designed to outlive it. The bright orange recorder protects the final evidence so that the cause of one disaster does not disappear with the wreckage, and so that what is learned from one flight can help make the next flight safer.